Hi students, in this video we're going to look at an introduction to anti-differentiation. So after watching this video you should be able to recognize anti-differentiation as the reverse of differentiation and also use the correct notation for antiderivatives or indefinite integrals. The biggest thing to remember is what we mean by a derivative or differentiation. So derivatives are the functions that represent the gradient of a tangent to the curve, or the instantaneous rate of change. So with some of our notation here, we use f dash x is the derivative of, using the variable x, some function. All right. When we think about anti-differentiation, that is just the reverse or the opposite or the inverse. Okay, so that's sort of those sorts of ideas. The opposite idea, the opposite steps. So in future videos, we'll go through how to anti-derive a bunch of the different functions we know how to derive. For now, we're just getting used to the idea. Now, in terms of applications, what we're thinking about here is, or the sort of questions we might be asking might include, if we know the rate of change of a function, can we work out what the original function was? So if we know the derivative, if we know the gradient or rate of change, can we work backwards and work out what the original function was? Or in a more practical situation, we might ask, if we know how fast a car is traveling, can we work out how far it has traveled? And we'll do an example of that later on in this series. But this idea of going from the rate of change function back to the original, that's what anti-differentiation is. Now, how we use our notation is we use capital F of x as our antiderivative. We have this symbol here. It's a curved S, elongated S. It means sum. We write our function next that we're anti-deriving, and then dx at the end represents the variable that we're deriving according to. Now, there is a whole lot going on here in this formula, and in a future video when we talk about integration, I'll explain what's going on there. But for now, we just need to know the notation. So capital F for our antiderivative, that long S-looking shape is our opposite or our integral, our antiderivative of our function f of x, and then dx on the end there. Now, before we start getting into some functions to antiderive or even looking at some graphs, we do want to consider the following functions. So we've got x squared plus 3, x squared minus 10, just plain old x squared, and x squared plus 10,928.23. Now, one thing to notice, guys, is that all of these functions have the same derivative. So the derivative of the first one is just going to be 2x, and the 3 disappears. For the next one, it's 2x again, and 2x again, and 2x again. Now, I can come up with any number at the back, any constant for these functions at the very back. The derivative is always going to be 2x. Now, it doesn't sound like a problem, and it's not a problem when we're deriving. In fact, it's quite nice to have our constants just disappear when we're doing differentiation. But if we want to go in reverse, if we want to work out the antiderivative of 2x, well, we know it's going to start off with x squared, right? So if we've got our derivative of 2x, if we want to go backwards, if we want to antiderive, we'll get x squared. But what number will be on the end? It could be plus 3, it could be minus 10, it could be nothing. It could be something random. We don't know what constant is on the end there when we're anti-deriving. It could be any constant, but the thing is we don't know what it is. And the main reason for that is because when we derive, the constants disappear. When we go back and anti-derive or anti-differentiate, we can't really know what the constant is without more information. So when anti-differentiating functions, we include a constant term c, and we call that the constant of integration. So when we do something like this one here, if we're integrating 2x dx, we write that as x squared plus c. And c could be any constant, 1, 0, 500, 300, negative, and 84.38. Who knows? That constant could be anything. We need more information to work out that constant. But we need to include that plus c to say that there could be some constant there. We just don't know what it is. All right, we've got, now let's do an example of anti-differentiation here. We've got some graph of f of x. We need to sketch a possible graph of the antiderivative f of x. All right, so some good places to start are just to work out what, some key points. So maybe this y-intercept, this x-intercept, that point at the end of our function, and here. Those are some key points in our original graph. Now, what f of x represents at the moment, we're going to call that our gradient function. Okay, so f of x is the gradient function of capital F of x. So what we're going to do is use this graph and get some ideas, get some tips for what the gradient's going to be. Now, we'll start at 0, but realistically with this function, we could start anywhere because we don't know what the starting point is. That's the point of the plus c, that's our constant of integration. So down here, our gradient is equal to -2. That's just reading off the bottom there. Here, at x equals 1, the gradient is -1. Here at 2, the gradient is 0. Here at 1, the gradient is 1. Also at 3, gradient's 1. Then at 4, the gradient is 2 again. So let's consider what that means here. So at our graph, it's going to start off with a gradient of 2, which will be sort of down to there. So it'll be steep, but the thing is it's getting less steep as we go. So it's curving a little bit. At 1, the gradient's going to be close to 1. And then at 2, the gradient's going to be is going to be 0. From this graph here, the gradient is ending up being 0 at x equals 2. So that's where we're flattening off here. And now all of a sudden our gradients are becoming positive. So at 3, our gradient was looking close to 1. And then at 4, it's now getting quite steep. It's almost looking a bit parabolic even. Now, for this next section from 4 onwards, that gradient's the same all the way through. So that's just a constant gradient of 1. So that's going to be a line with a constant gradient of 1, which will look like this, but should actually be a line. And then if we check it, all right, apart from my messy sketch, it's got the right sort of idea. You've got that steep gradient of 2 at the beginning, evening off to 0 at x equals 2, going back upwards to 4, and then that straight line at the end there. And that's how we can sketch a rough antiderivative from a function. Students, after watching this video, you should be able to recognize anti-differentiation as the reverse of differentiation and use the notation for antiderivatives or indefinite integrals.